Find all pairs of primes, p and q, for which p minus q, and pq minus q are both perfect squares. We let p minus q equal m squared, and pq minus q equal n squared, where m and n are positive integers. Then n squared minus m squared equals pq minus q, minus p minus q. By simplifying, we have n squared minus m squared equals p times q minus 1. Because q is a prime number, so q can take values 2 or 4k plus 3, where k is a non-negative integer. For example, when k equals 0, then q equals 3. When k equals 1, then q equals 7. Or 4k plus 1, where k is a positive integer. For example, when k equals 1, then q equals 5. When k equals 3, then q equals 13. So we divide the problem into 3 cases. Case 1, q equals 2. Then q minus 1 equals 1. From equation 1, we know p equals n squared minus m squared, which is equal to n minus m, times n plus m. Because p is a prime number, so the only factors of p are 1 and p. And because n minus m is less than n plus m, so n minus m equals 1. And n plus m equals p. 2m equals n plus m, minus n minus m, which is equal to p minus 1. So m equals p minus 1, over 2. As p minus q equals m squared. So p minus 2 equals p minus 1, over 2, all squared. Multiply the equation by 4, we have 4p minus 8, equals p squared, minus 2p plus 1. So p squared minus 6p plus 9 equals 0. That is, p minus 3 all squared equals 0. So p equals 3. So p, q, equals 3, 2. Verify whether this is a solution. P minus q, equals 3 minus 2, which is equal to 1, which is 1 squared. Pq minus q, equals 3 times 2, minus 2, which is equal to 4, which is 2 squared. Thus, p, q, equals 3, 2, is a solution. Case 2, q equals 4k plus 3, where k is a non-negative integer. Now substitute q equals 4k plus 3, in equation 1. We have, n squared minus m squared equals 4k plus 2, time p. Clearly, which is congruent to 2, modulo 4. As m and n are positive integers. So there are 4 possibilities. Either, m and n are both odd. Let n equal 2i minus 1, and m equal 2j minus 1. Or n is odd, and m is even. Let n equal 2i minus 1, and m equal 2j. Or n is even, and m is odd. Let n equal 2i, and m equal 2j minus 1. Or, m and n are both even. Let n equal 2i, and m equal 2j. Where I and j are positive integers. For n equals 2i minus 1, and m equals 2j minus 1. n squared minus m squared, equals 4i squared minus 4i, minus 4j squared, plus 4j. Which is congruent to 0 modulo 4. For n equals 2i minus 1, and m equals 2j. n squared minus m squared, equals 4i squared minus 4i plus 1, minus 4j squared. Which is congruent to 1 modulo 4. For n equals 2i, and m equals 2j minus 1. n squared minus m squared, equals 4i squared, minus 4j squared, plus 4j, minus 1. Which is congruent to 3 modulo 4. For n equals 2i, and m equals 2j. n squared minus m squared, equals 4i squared, minus 4j squared. Which is congruent to 0 modulo 4. We have shown that n squared minus m squared is congruent to either 0, or 1, or 3, modulo 4. However, if q equals 4k plus 3, then, as we have shown, n squared minus m squared is congruent to 2 modulo 4. This is a contradiction. Therefore, there are no solutions when q equals 4k plus 3. Case 3, q equals 4k plus 1, where k is a positive integer. Now we substitute q equals 4k plus 1, in equation 1. We have n squared minus m squared equals 4kp. As k is a positive integer, so we let k equal u times v, where u and v are positive integers. And u is greater than or equal to v, which is greater than or equal to 1. Then equation 2 can be written as n minus m times n plus m equals 4p times u times v. Because n plus m can be written as n minus m plus 2m. So n minus m and n plus m are same parity. Because 4p times u times v is even. So n minus m and n plus m are both even. Because p is greater than q. And we assume that q equals 4k plus 1. So p is greater than 4k, which means p is greater than 4u times v. All these give two possibilities. n minus m equals 2u, and n plus m equals 2pv. Or, n minus m equals 2v, and n plus m equals 2pu. For n minus m equals 2u, and n plus m equals 2pv. We have m equals pv minus u. Then p minus q minus m equals p minus 4uv minus 1 minus pv plus u, which can be written as negative p times v minus 1 minus 4v minus 1 times u minus 1, which is less than 0, as u and v are positive integers. This implies that p minus q is less than m. For n minus m equals 2v, and n plus m equals 2pu. We have m equals pu minus v. Then p minus q minus m equals p minus 4uv minus 1 minus pu plus v, which can be written as negative p times u minus 1 minus 4u minus 1 times v minus 1, which is less than 0, as u and v are positive integers. This implies that p minus q is less than m. So far, we have shown that if q equals 4k plus 1, then p minus q is less than m. This contradicts p minus q equals m squared. So there are no solutions when q equals 4k plus 1. Therefore, p, q, equals 3, 2, is the only solution.